in Chapter 7, we'll be working with statistics. The first unit, we'll be looking at collecting and graphing data. Statistics began in the 17th century. We give John Grant of England credit for developing the concept of statistics and pointing out the need for collecting statistical information. He found that if he collected information about births and deaths, the cause of deaths, that he could use that information to better society. And he published a book called Natural and Political Observations of Mortality, and from that he was able to begin spreading the word for how valuable it can be for us to log information and keep information about things like the bubonic plague and the number of women who die of breast cancer each year, or the number of men who contact mesothelioma by working in asbestos, or on and on. The need and use of statistics began in about the 17th century. There are two types of statistics that we will be looking at. One is descriptive statistics, where we take the summary of data and make it understandable. The other is inferential statistics, and that's where we make a conjecture about a large population based on sample sizes. So if we take 10 major cities in the United States and we sample 5,000 people in each city, and then we make a prediction about all people who live in the city, we're using inferential statistics. If you look in your textbook on page 438, we have our problem opener. And you see two different line plots. One of these represents the number of cavities that students have in a particular class, and the other represents the number of families, or number of people in a family. And so by looking at the two, we can choose which one describes that information. We would hope that there would be many students in the 4th grade that have no cavities. However, we would not want this many students in the 4th grade to have no family members. And so we see that in the first 4, it's where most of the information is, and we would not want 4 cavities for most of the 4th graders. However, 4 members of the family would be appropriate. The National Council of Teachers and Mathematics standards say that by the end of the second grade, students should be able to organize and display their data through both graphical displays and numerical summaries. They should use counts, tallies, tables, bar graphs, and line plots. So you will find that from the second grade on, you are beginning the study of statistics. Now, bar graphs, a second grade concept. If you'll look in your textbook on page 438, we have some information about 40 teachers. They're in favor, opposed, or they have no opinion about whether the end of the school day should be 1/2 hour earlier. If we leave this information in a table as it is written here, we find that it's hard for us to tell how many are in favor and how many are opposed. So by organizing that information into a bar graph, it makes it very easy for us to judge those in favor, those opposed, those with no opinion. So by putting the bar graph, we immediately, without thought, have a count. A bar graph has a title. The bars are the same distance apart and they do not touch. We have a title for the horizontal and we have a title for the vertical. And so now we know that 18 teachers were in favor and 14 were opposed. This is a single bar graph, but sometimes we like to show how one bit of information compares to another. And in this bar graph, we're looking at children reporting no physical visits in the past 12 months by age and race, ethnicity. So we see that the horizontal represents age and the vertical represents the percent. Also, there has to be a place, a legend on the graph somewhere to represent what each color stands for. They have chosen to put that inside. Often you have a legend to the side of the graph that shows that the blue represents white, the red represents black, and the green represents Hispanic. And so by age, under the age of 4, we see that the Hispanics, 7 1/10%, would be the most number who have not had a doctor's visit in the past 12 months. Continuing to look at the graph for every age category, we can see that the Hispanics, according to this example, would be the group that has not visited a physician in the past 12 months. So if we were to use this to make some predictions about how we should change our health care or how we should target different people in our population, we could use this as a helping tool to improve our environment. In the next, we are going to look at making a pie graph. You will need a compass and a straight edge. So if you will get that ready, I'll give you a few minutes of time to get your compass and straight edge. Our pie graph is often called a circle graph, or can be called a circle graph. It's called pie because it's shaped as a circle and divided into sectors so that it looks like a piece of pie. The circle represents the whole, and each section of the pie represents the part or the proportion. So we're going to look at how we can create a pie graph. So the first thing we want to do is to make a circle with your compass. Now I'm using what is called an angle ruler. And the angle ruler not only is measured in inches and in centimeters and millimeters, so it's a ruler, but it also has a compass and it has a protractor. So I can make circles using, I have to have two pencils. So I use one pencil to hold the center, and then I use these holes to make the circle. And then here we have the protractor where I can measure the angles. These are a little more expensive, but you get three things in one. So I like them. Actually, what I like are those old-fashioned compasses that have the sharp points, but now I think you would not get away with having those in your classroom. But they're my favorite. I taught with them for years and had no accidents, but I can see that you might have someone stab another and then there you'd be in a pickle. Alright, so I'm going to make a circle. So with your compass, make a circle. This is the negative part of the angle ruler, is that your circles don't always meet because it's easy for them to slip. I'm going to be sure to mark the center of the circle. And I'll go ahead and make a radius. Now I know that a circle is 360 degrees. So whatever portion of that circle belongs to a category, then that is exactly that many degrees that you have to make this central angle. So going back to our teacher problem, we said that there were 45% that were in favor. So I'm going to set up a proportion saying 45 out of 100 would be how many degrees out of 360. Now in Math 231, we had a no calculator. But in Math 232, you're going to be very glad that you can use a calculator. So you need at least a scientific calculator. Do not have to have a graphing calculator. They're nice, and I will show you how to use one, but you can get by with a scientific calculator. If you have to go out and buy one, be sure that you can do standard deviation on there. Alright, so I'm going to do cross products. You know, that's the product of the extremes is technically what we're doing. So we're taking 360 times 45. Cross products. So I have an equation. 16,200 is equal to 100x. And then I'll divide both sides by 100. And I have x to be 162. So that means the portion of the pie that will represent those in favor should be 162 degrees. Now you know that 45% is about, 45% is about 1/2. So we would expect the number of degrees represented in the circle to be about half of the circle, which 162 is near 180, which would be half. I'm going to put the center of my protractor at the center of the circle and the 0 on the radius, and I'm going to measure around to 162 degrees, and I'm estimating. Looks like maybe I'm in the ballpark. And another purpose for the holes on the angle ruler is now once I get my 162 degrees, I can make a point in that hole, and I now can from the center make that new radius. This represents 45% of the circle, almost half. And this central angle is 162 degrees. We label those in favor. there were 35% opposed. So we set up a proportion. 35 over 100 is equal to how many degrees out of 360? So I do cross products. 360 times 35 is 100x. I divide by 100. And 126 degrees is the value of the next section of the pie. Now, if you're having trouble remembering how to use a protractor, you can Google, and there's some very nice detailed instructions and examples where you can find help for that. We will study that later. We have a unit on geometry, so we'll look more at this. And now we have our next piece of the pie. And that central angle should be 126 degrees. And this is the 35% that are opposed. And what's left over has to add to 360 degrees. And so this should be 72 degrees left. And you can measure that to see if you have about 72 degrees. And these represent the no opinion. And that is about 20%. I believe in our lab we do another pie graph, so we'll get another chance at making one in our lab 7-1. Students typically have trouble with this. I think setting up a proportion in calculating the number of degrees that you measure the central angle is helpful than trying to do other methods. So I like setting up the proportion. Also, this needs a title. So we're going to need to title it as Teacher Responses to Changing Hours of the School Day. So a title as well as the percent, as well as each sector labeled as not only the percent but what the percent represents. Typically you do not see these angles. I wrote those angles in just to help you see what I was measuring, but these are not a part of the graph. Pictographs are another way to show a summary of data. We take little icons and we represent the value. So they typically they look like a bar graph. The problem I see with a pictograph is when they start trying to represent portions of an icon, it's sometimes difficult and you lose the exact data. It's easy to see increases and decreases. So whatever value that a bar graph has, I guess the pictograph has, in that I can quickly see. Now I'm on page 442 in your textbook. I can quickly see when I'm looking at juveniles aged 10 to 17 that were arrested for drug abuse. I can easily see that in 1991 and in 1990 we had some good things going on. Well, I hope it was good things going on. Either our teens were getting smarter and not getting arrested, or hopefully we had some drug intervention program targeting these teens so that the drug abuse was actually at its lowest level. But what happened in these years after? It seems either we're getting smarter at catching them, or the use of drugs is becoming greater. And so we can get a trend for the data. We actually kind of lose the data, the precision of the data, because if you notice, each of these icons represents 10,000. So we're rounding these columns to the nearest 10,000. So I'm okay until we start dividing these into fourths, and so we have an icon with just legs, or we have an icon with the body and no head, and you're trying to estimate, okay, how much of that icon is there? This example doesn't show that. It has whole icons, and I can deal with that. However, you're rounding to the nearest 10,000, so that's a pretty big gap there. Frequency is a term that we use that represents how many you have. If you like Wheel of Fortune, you might like to do this activity in your class where you give students a phrase, a paragraph, whatever, and you have them count how many letters or how many times A appears in that phrase, how many times B appears, how many times C, and so on. And when we do this, we are getting a frequency count. Often we write our frequency count using tally marks, and we go with, whenever we have 5, we use 4 lines and a mark through it. It's suggested that this began in England when they were trying to keep track of how many beers that someone had drunk, and this is how they keep tally. They do 4 lines and then a mark through it. So that's how we also will represent our tally marks. So in this example where we have 5, 10, 15, 20, so this would represent 22. So if I had the phrase, "We the people of the United States," then this would be an example of the tally marks. Now, you might not be able to see this clearly, but what I do want you to see is the overall shape. Notice that the shape of the tally marks can also represent the shape of, if I turn it this way, we are beginning to see an idea of a curve being formed in the data. The term data can either be singular or plural. These are just more examples of tally marks, and this shows a frequency table where we take the tally marks and we actually count the numbers there and we put that number in the table. So this is a frequency table. This shows the letter A occurred 3 times in 7 years ago. The letter C 1, the letter D 1, and so on. Now, another way of showing that after we've done our tally marks, after we've done our frequency table, is to use what some people call a dot plot. Your textbook calls it a line plot. Now, the advantage of this line plot is you can see how the data falls, you can see gaps in data, and you can see where there are clusters and where there is unusual data. So in this problem showing test scores for a math class, we can see that most of the data is falling in the 80s and 90s. There is one student that got a 98, and that's pretty unusual compared to most of the data being here. And another student got a 68, and that too is unusual. That's unusually low. This is a little bit high compared to what most of the class did. So that's how you can make advantage of that line plot as opposed to the bar graph or the pictograph or the pie graph. In those first 3 that we looked at, we are losing the original data. We are looking at categories. But in this line plot, we are keeping every score and plotting it onto the graph. So you're preserving the original data. And again, it makes it very nice that you are able to see where most of the values occurred and where the least values occurred. So I have several other examples of dot plots and showing you how handy that they are. This is showing a traffic study, and it's showing the number of cars that pass an intersection within a half-hour time. So if we look at when they arrived, most cars, or the busy time, was between 8 minutes and 12 minutes. So whatever time they were there, oh, you're not even seeing it, sorry. So the busy time that they were there is between 8 minutes and 12 minutes. When they first got there, the first couple of minutes, no one came. And then after 4 minutes, a car came. After 5 minutes, a car came. And then it begins to get really busy. And then it begins to taper off. So this might be the time that parents are dropping students off to school. In this dot plot, we're showing rim size of tires that are sold by a warehouse. You can see that if you're trying to judge the kind of tires that you want to have in your warehouse so that you're have a good supply, or you have supply ready to meet the demand, that you're going to want to have more 15-inch rims, and no one wanted a 19. So you might have very few 13 and 20, no 19, very few 18, most 15, and then several 14 and 16, and then a few less of 17. If I wanted to buy, let's say, a camera, and I'm looking at different brands of cameras and the number of defects out of 50 cameras sold, how many cameras were defective, then I'm going to want to buy this camera, the one that had 0 defects. Or 1. So it looks like most of them occur on the 0, 1, and 2. I definitely would not want to buy the camera that had 4 and 5. So I like dot plots or line plots because they preserve the original data. It gives us an overall feel for where most of the data falls, where the gaps are, where the unusual data is. And so that is the wonderful property of a line plot or a dot plot. The examples I showed you use dots. Your textbook uses X's. It does not matter which you choose to use. The next plot we want to look at is the stem and leaf plot. They too preserve the original data, so that if we're looking at numbers, the stem part of that number would represent the tens place of this, and the leaf part would represent the ones place. Data that is repeated, like there were 2 70s, is also repeated. So a 0 0, the 74s repeated twice, so the 4s are written twice. We don't put commas between them. We just write them out, and each of these represents one's place of the data. Now, again, if I turn this way, we can get kind of a picture like we did for the dot plot. We definitely can tell that most of the data falls in the 70s and 80s. 45 would be unusually low compared to the rest of the data. So we could even make a general statement saying most of the data is 70 or above. We have a little bit of data in the 60s and below. So this begins to give us a shape. The data begins to take shape. Another example, we have our data. We put our tens place to be our stem, and then we put our ones place to be our leaf. Notice that there are no 60s, so we can't put a 0 there because that would mean that you have the data value 60. So if there are no 60s, we put a 6 in tens or in the stem column, but we put nothing for the leaf. You can see an advantage to taking information that's written in a chart. This is the gross opening weekend box office receipts for movies. The receipts are in millions. But notice that we start with our stem at the lowest, which is 30, and go to our highest, which would be 11, and then our ones place, what that allows us to see quickly is if we turn our sheet sideways, we get a trend. We see that most of the data is falling in below 50 million. So we would expect most movies to earn 50 million and even more often in the 30 million. It would be really unusual for it to be over 70 million, and even more so over 100 million. Matter of fact, only 2 movies were over 100 million. And that's Spider-Man 2 and Shrek 2 at the time this was made. So, like the dot plot, the stem and leaf plot is very handy as it preserves data. It also gives us an idea of gaps and trends for data. Next, we want to talk about a histogram. And a histogram is made up of bars, but the bars are going to touch each other. And the vertical bar will tell you a frequency. Now, I've already talked to you about a frequency table. Now we count how many times an event occurs. So the vertical bar on a histogram will tell you how many times that the event happened. Now we group the data into intervals like you do on the bar graph, but the bars will touch on a histogram. So that will be your first clue as to whether you have a bar graph or a histogram. Do the bars touch or do they not touch? If you're given data like you have on page 445 in your textbook, by the way, before I go on, you can have a stem and leaf plot that compares 2 sets of data. The stem would read 45, 57. This would represent one set of data. And then the stem would read, going left, 49, 55, 52, and so on. So you can have a stem and leaf plot comparing 2 sets of data. Another thing I want to say to you on this before I go on, the leaf part is written in ascending order. So you're going from 2 up to 9, from 0 up to 5, 2 up to 7, and so on. Alright, now back to our histogram. We're looking at, in this group of data, the gestation period for 42 species of animals. When we see them written like this, it makes it difficult. We might scan through and see which would have the shortest, which would have the longest. But it's hard to compare them. In organizing the data into a histogram, we need to figure out what the shortest gestation period is for any animal. And as I scan down through here, I can see that a possum would be 15 days. And I guess that's the shortest. And then I look for the longest And that might be the rhinoceros at 498. Then you need to decide how many categories you want to have. Or how many intervals, how many bars do you want on your graph? You want 5, you want 8. If you're making the bar graph, that's your decision to make. We don't want too many and we don't want too few. So typically, if we can keep within 5 to 10, we will take the least, which was 15, and the greatest, and we'll subtract them. So we have a difference of 483. If I decide I want to have intervals of your textbook used 10, but you could use, if you wanted to have 5 bars or 8 bars or 10 bars, that's what you're going to divide by. So this would be about 48. So anything that had a gestation period from 0 to 48 days would go in bar 1. And then from 49 to, add another 48 onto that, 97, that would be in bar 2. And add another 48 onto that, and that would be bar 3. And so on. Then you have to set up a frequency table to see how many would fall in that category. How many fall into the 0 to 48? How many fall into the 49 to 97? And so a good way to do that is to set up your tallies. So if I go 0 to 48, and 49 to 97, I'm going to go through, and the ass is 365. So when I come to that, I'll put a tally mark and mark off. Then the baboon is 187. I'll go down to that, make a tally mark, and mark off. That way you don't leave any out. So they have the frequency table made. And then this is what it would look like. The number of animals that are in that category makes up the vertical bar. This is the count of species of animals. This is the number of days of gestation, and it has a title, Gestation Period of Animals. This is on page 446. We divided by 10, so we have 10 bars. I've lost my original data in the histogram, but I've gained an idea of where most animals' gestation period lies. It looks like most are within the 0 to 300 days. A line graph, different than a dot plot or a line plot. A line graph connects with segments, the points, so that you get a trend. So by looking at how steep that line is, we can tell when things changed quickly or when things changed slowly. So we can see that from 1800 to 1840, the U.S. population grew, but it grew slowly. Where the line is the steepest, that's where we had the greatest increase in population. Now notice that this represents a count in millions of people, and this represents years, and it does have a title. Another way of representing data is by use of a scatter plot. Now, in a scatter plot, you have ordered pairs of data. So in the example in your book on page 447, we see that we're comparing a student's height to their shoe size. And we want to see if there's a relationship between a person's foot and how tall they're going to be. I put height on the horizontal and I put shoe size on the vertical. It has a title. And we plot it as ordered pairs. If the trend of the data is increasing like it is here and it's clustered close together, we say that there is a relationship between the height and the shoe size of 8th grade boys. I can draw a line that I think models where half of the data would be above it and half of the data would be below it. And that line is called a trend line. And if that trend line is increasing as you read it left to right, we say there is a positive correlation between shoe size and height. If the line went this way, we would say as a person's foot gets bigger, they get shorter instead of taller. So on the next page, we see a trend line that models half of the data above, half the data below. Sometimes we plot data and the data is just all over the place. There is no pattern. and we say there's no association. So if I look at, the amount of corn I eat for dinner compared to the number of shoes I have, there might be no relationship between that, and the data would be all over the place. So that's no association there. And then we already saw the positive correlation, where as the foot gets larger, the height gets taller. Both of them increase at the same time. And this shows a negative correlation. An example I can think of a negative correlation would be if I begin eating a candy bar, the longer the time goes, the less I have. So as time increases, the size of the candy bar decreases. And that's negative correlation. As one thing increases, another decreases. The example they give you is from the starting point at time, they're dealing with age. This is age of children, and this is time in seconds. So a student that is 5 took about 11 seconds, and a student that is 11 took about a little more than 4 seconds. So the younger you are, the longer it takes. The older you are, the less amount of time it takes. So as one gets bigger, the other number gets smaller. And that's showing a negative correlation. Now we can use calculators, graphing calculators, that will plot a scatter plot for you, and they will also determine the line of best fit. They will also give you an equation for that line. And a correlation coefficient. The correlation coefficient is the R value on the calculator. And if that R value is near 1 or negative 1, that means that there is a strong correlation. So I would say, when we were looking at the data of the 8th grade boys, that we would probably have an R value, I'm just guessing, maybe at 9/10, which is close to 1. So we would have a strong correlation between shoe size and height. If the R value is 0.25, it's positive, but it's not a strong positive. Alright, that is the end of the lecture. I suggest that you look over problems on page 454, 7.1. The odd problems are in the back of the book, so you can work some and then check your work. And then after you've done your lab and after you've done your guided notes, then you will be able to take your first quiz. So I will see you at lab time.